So the TM waves in rectangular waveguides. Can you relate the figures? Waveguides. A waveguide is a special form of transmission line consisting of a hollow metal tube. The tube wall provides distributed inductance while the empty space between the tube's wall provides distributed capacitance. Waveguides are practical only for signals of extremely high frequency where the wavelength approaches the cross-sectional dimension of the waveguide. Below such frequencies, waveguides are usual as electrical transmission lines. The two types of waveguides are rectangular waveguide and circular waveguide. The rectangular waveguide is mostly preferred type. The frequency difference between consecutive modes are smaller, and circular waveguide is less preferable, in which polarization not maintained and circular symmetry. A rectangular waveguide. Consider a rectangular waveguide of width A and breadth B. An EM wave is assumed to propagate in Z direction as shown in the figure. The boundary conditions for rectangular waveguide is Ex equal to 0 and Ez equal to 0 at y equal to 0 and y equal to b, and Ey equal to Ez equal to 0 at x equal to 0 and x equal to a. Analysis. We are going to take the Maxwell equations del square E plus mu epsilon E omega square equal to 0 and del square h plus omega square mu epsilon h equal to 0. From del cross E equal to minus mu dou h by dou t, we are forming the matrix and equating the equations. We get dou Ez by dou y minus dou Ey by dou z equal to minus j omega mu hx, and dou Ex by dou z minus dou Ez by dou x equal to minus j omega mu hy. Dou Ey by dou x minus dou Ex by dou y equal to minus j omega mu hz. From del cross h equal to j omega epsilon E, we are forming the matrix for del cross h and equating it with j omega epsilon E. We get dou hz by dou y minus dou hy by dou z equal to j omega epsilon ex, dou hx by dou z minus dou hz by dou x equal to j omega epsilon ey, and dou hy by dou x minus dou hx by dou y equal to 0. Activity. TM waves in which hx and ey equal to 0, ez, ex and hy will have values. So hy equal to c3 sin hx plus c4 cos hx e power minus gamma z. The boundary conditions cannot be applied directly to evaluate c3 and c4 because the tangential component hy is not equal to 0 at the surface of the perfect conductors. So Ez equal to 1 by j omega epsilon dou hy by dou x, which gives the values Ez equal to h by j omega epsilon into c3 cos hx minus c4 sin hx e power minus gamma z. Applying boundary condition 1, we get c3 value is equal to 0. Therefore Ez becomes minus c4h by j omega epsilon sin hx e power minus gamma z. Applying boundary condition 2, that is Ez equal to 0 at x equal to a, we get Ez equal to minus ac4 by j omega epsilon sin ha e power minus gamma z. To make Ez equal to 0 at x equal to a, we substituting the value h equal to m pi by a. We get Ez equal to minus m pi by a c4 by j omega epsilon sin m pi by a x e power minus gamma z, and hy equal to c4 cos m pi by a x e power minus gamma z. Similarly, the other fields are obtained. So substituting gamma equal to j beta for wave propagation, we get Ez, Hy, Ex values as shown in this slide. The above equation are fields of TM waves between parallel planes. Thank you.